Okay, so moving on. So we were talking about the u-substitutions, right? And we had just kind of gotten into that and we're practicing and we got through quite a few. Let's look at one more u-substitution and then, well, one more kind of easier one. And then I want to show you how you deal with incomplete substitutions. We'll look at that. And then hopefully today we'll get a jump on what happens if we have a definite integral? How do we deal with u-substitutions with a definite integral? And it doesn't really add very much. Okay, what about this guy? Stare at that for a second. Think about this. What is my u-substitution going to be here? What do you think? Suggestions. And remember, you want to pick your u so your du matches what's going on here well also. Think about what has to be true of your du. It has to be in the numerator, right? You could never do an integral. We never would have that's always multiplied by the integrand. And so it could never be like in the bottom. It could never be to a power. It just has to be a plain old du, to within a constant. So what do you think? Becky, you look like you have an idea. What is it?
Would we want to do e to the x or e to the x plus 4? Because some of the derivative is e to the x.
Right. So which one do we want to do? E to the x plus 4. Yeah, for two reasons. Because its derivative is going to simplify to e to the x dx, right? But also because it's in the denominator, right? Stuff that's in the denominator would have to be a logical choice for a u there, wouldn't it? So u is going to equal e to the x plus 4. And then what is the derivative of e to the x plus 4? E to the x dx, right? Because we're writing it in differential form. Okay. So then what do we got? Well, it looks like we've got a direct substitution here, don't we? There's our du right there. And there's our u right there, right? So this ends up just looking like, when we make our substitution, the integral of du over u, which is equal to what? What is it? Yeah, natural log of u, right? Okay. And we'll just reverse the substitution. And so we get natural log of e to the x plus 4, right? What's that? Because that's just that's standard form. Oh, man. Hey, it's my wife. I've got to take this real quick. Hang on. Right. That's one we know. I mean, that's just in our table. Okay. We're just trying to get stuff that's in our table that we know. Okay. Make sense? Okay. So what about stuff like this then? Incomplete substitutions. What would my choice of u be here? What do you think? Everybody think about it for a second. What do you think, Tori? What would you probably pick for your u?
Square root of 4 plus x.
Probably not the square root part, right? Because if I pick u to be a square root, then when I differentiate, I need to have I'm going to have like a square root as part of my du, and we don't have that, right? So it's just going to be the 4 plus x. And again, how does our intuition tell us that? I mean, you don't have a lot of intuition on this stuff yet, but you're going to start to see that your u substitutions are typically going to be the arguments of the more complicated looking function. So if I've got a square root there, Yeah, whatever's inside that's probably a good bet that might be u. And do you have to get it right on the first time? No, you don't. I mean, doing these things, eventually you're going to start to get better at it, and you will get it right on the first time. But sometimes, you try a u and it doesn't work, so you try another one. And eventually, there's some stuff that we'll do where u-substitution may not be enough, and we have to go to a different strategy. There's a bunch of other different strategies we have for evaluating definite integrals, right? I mean, we don't know what those are, integration by parts, or trig substitutions, or there's all these method of partial fractions. There's all these other methods that we'll learn. We won't get to all those this year, but we'll get to a couple of them at least. Okay. So yeah, our good choice for u would be 4 plus x. And so then what's du? If I differentiate 4 plus x, what do I get? Dx. Yep. Okay, so that works out well, right? So then what do I get? Well, I've got inside the square root, I'm going to have a u, and then I've got a dx at the end. But what's the problem with that? Yeah, look at that. We still have, if we do that, we still end up with, whoops, I guess I don't want to do that. I've still got an x there, right? So this looks like the integral of the square root of u is the same thing as a u to the 1/2 times, gotta get my colors right, don't I? That's a u to the 1/2 times a du, but I've still got that x there. So that's what we call an incomplete substitution. We want to get all of the x stuff to turn into u stuff. What do you think we could do to complete that substitution?
Can you solve for x?
There it is. I could just solve for x up here. Just isolate the x in terms of u. Is that always something you can do? Well, sometimes it's tough to do, because sometimes, like this worked out great, but sometimes the x might be tied up inside some other types of functions, which makes it very difficult to isolate the x. And so that would be an instance where probably u-substitution isn't going to work, right? There's probably a better way to do it. But for this guy here, yeah, we just solve for x, and x is equal to u minus 4. So now we can make that substitution, and look what happens. We get the integral of the quantity u minus 4 times u to the 1/2 du. And you might be asking yourself, well, what did that accomplish? Right? We still end up with a product of two things, but I would argue that this is a way better product to deal with than that was. You see why? Because look, I can distribute the u to the 1/2 to both terms and just get two separate power functions that I can integrate with the power rule, right? I can't distribute here because the 4 plus x is inside of a square root, and I can't distribute over a square root function. Everybody see that? Okay. So what did it allow us to do? Well, it just changed the form in a way where now this is convenient, right? Now we could distribute, and we would get the integral. If I distribute the u to the 1/2, I'm just going to get the integral of u to the 3/2 minus 4 u to the 1/2 du, right? And that's one we can do. So what do I get for, what's the antiderivative of that first part? What's the integral of u to the 3/2 du? Okay, u to the 5/2 times 2/5, right? Divided by 5/2, but we'll just multiply by 2/5, right? Same thing. Same thing. Yep. Integral and antiderivative mean the same thing. Yep. And then the other one's going to be, see, I've got integral of u to the 1/2 is 2/3 u to the 3/2, right? So I'm going to get an 8/3. Does that all make sense? Everybody good with that? So then what do I have to do? Just, I don't know, I mean, just last step would just be to distribute the, or not distribute, to reverse the substitution and just trade those u's for the quantity 4 plus x. and we're done, right? Oh, what happened there? Huh. Yeah.
For both of them. Because,
How do we get 5 halves?
yeah, for both of them.
Oh, we shouldn't. That should be 3 halves. Yep, you're right. That should be 3 halves. Whoops, we got to change that. Yep, that one's. Oops. Right? Okay, and then that's where all that stuff came from, I guess, right? Everybody see that? There's all the work. But those guys didn't get. Let me do. I think there's a way I could be really tricky with this. There, that should work. There we go.
Oh, well, it'd be different because we changed.
Okay, everybody good?
So,
Okay. So we had to complete the substitution there on that guy. Questions? How'd I what?
How does it go to 4 plus x?
Well, because that's what u is, right? We can't leave our answer in terms of u. Problem is expressed in terms of x.
Oh, okay, yeah, that makes sense.
Okay. Question. What's that? Yeah. Yeah. You're simplifying, or you're taking the integrals, what we would say in calculus, right? Okay. All right. Let's try. Okay. Now, what about these? So, I want to just show you here real quick now how we could come up with the other missing standard forms that are on our integral table, right? Like if we want to integrate tangent of u du, what do? Well, we're just going to let's make it a tangent x instead of tangent u, and then we'll at the end, well, whatever our answer is, we'll write it in terms of u's for our table. Tangent of x, we know how to do this, right? That's just sine x over cosine x. That would be your first impulse anyway, probably, right? It would be to write it in terms of sines and cosines if you need to. Well, then we could make the substitution. Let's let u equal cosine x. And so if u is cosine x, then du would be negative sine x dx, right? So what do we have then? We've just got a 1 over u times negative du. We could pull the negative out front, and I've got the integral of du over u, which is natural log, right? Natural log of the absolute value should be, right? So then we end up with negative natural log of the absolute value of u plus c, reverse the substitution, and we got it. It's just negative natural log of the absolute value of cosine x plus c, which is what's on our table, right? Okay, and we could do that with secant x, it's a little bit tricky. Why would you do this? Well, we're going to multiply both the top and the bottom by the quantity secant x plus tangent x. Why are we doing that? We're doing that so we could make the u substitution. If u equals secant x plus tangent x, then look what happens on the top. We get secant squared x plus secant x tangent x. Those just happen to be the derivatives of secant x and tangent x, right? So that's a really tricky step, but that's how you would do the proof. This is one where you would just multiply secant x by 1 in that form. But when all the dust settles, smoke clears, this is what you're left with. Okay. Oh, what'd I do? Well, I hit that button, didn't I? That's what I meant to do. Yeah, there we go. Okay. Good? Okay, so I'm not going to write out those proofs. I mean, now they're in the notes. You can look at them if you want to. But now we've got those. Now we have everything. And we could do the same thing with cotangent and cosecant. just parallel proofs for those two. Same kind of thing. Yes. You do, but you may not have. I just reprinted them the other day. There's one. You can just have it. There you go. Okay, so then next issue. Oh yeah, okay. I want to do some couple tricky ones. So what about this one? Now this is you got to be thinking about this in terms of the stuff that we did with inverse trig functions. These are the hardest standard forms to apply, no question about it. Okay, so this looks like du over 1 minus u squared, but what do we have to do to get there? What do I have to do to make this look like that? Because that's convenient, right? If you look at your integral tables, let's see here. I think, where is my integral table for this? There's one, okay. What's the standard form that we want to use for this guy? Which one are we using? Well, actually, the way they're doing it, we don't even have to write it this way, right? We could use this in terms of A's and U's. So I think the way I did this is the way I always do it, but let me just see something here. Yeah, we could do this a slightly different way, couldn't we? Let's do that. Let's do this so we're just using our tables. Tell me what number on there is the one we're going to use. Uh, 19, not 19. Which one? It's 18, isn't it? Yeah, it's 18. Good. Okay, so let's. If we had more time, I'd show you how you can do. Like the way I always like to do this is make that a 1, but not necessary. Okay, so we could do this if we let A equal, right? If we let A equal what? No. Look at 18. How are we going to match that integral on the table? 3. Okay, so if A is 3, what would U equal? 2x, okay. Right? Oops, let's make U blue. So what's du? What is it? No. U is 2x, so what's du? 2 dx. Okay, good. And look what we have up here. We have a dx, right? So dx is then equal. I guess we could write this step down. God, what did I do here? I always hit the wrong button, don't I? So then we could write this. I need to move these things around a little bit. So if we solve for dx is just 1/2 du. Everybody agree? So if I make my substitutions then, what does this look like? Okay, well this looks like the integral of dx is equal to 1/2 du divided by the square root of a squared minus u squared. Well, that matches our form, doesn't it? Right? What's that equal to? Well, that's just equal to 1/2 times the arc sine, right? Arc sine of u over a. I need a 1 over a though, don't I? Isn't there a 1 over a in our answer? No, there's not. Never mind. It's just arc sine of u over a of so what's that become? 1/2 arc sine of u is just replaced by a 2x, and a is replaced by a 3. So there's my answer, right? Okay, everybody good? Right? How do we know that's the answer? Because that's the integral that's on our table, right? Those are just ones that we just have to memorize. Yep. Yeah, yeah, 1/2. Right, we can pull constants out in front of integrals. Doesn't matter where it's just a factor of 1/2, so we can, right? We can, okay. Everybody see that? Okay, do you really need to put that a as 3 in there? I'd say you don't. I'd say we could just write that as 3 squared minus u squared. And then our answer would have been the arc sine of u over 3. I don't think you really need to write a equals 3. I think you just write it as a number square, constant squared, and then you know that a represents the constant that's being squared. Okay. Question? Well, because this has to fit the form a squared minus u squared, and 4x is the same thing as the quantity, or 4x squared is the same thing as the quantity 2x squared. Right? So it's 3 squared minus the quantity 2x squared. So a is 3 and u is 2x. Okay? Everybody see that? I gave you one like that to do, I'm sure. So you'll get a little practice with an inverse trig one. Okay, so next issue. Okay, this you're probably thinking, oh my God, this is going to be really tough. Okay, here, this actually makes it easier. When you're doing definite integrals are easier to do with u substitutions than indefinite integrals are, because what you're going to find is you never have to reverse the substitution. Show you what I mean. So what would the most appropriate u substitution be here to make this a relatively easy integral to do? Yeah, whatever's inside the cube function, right? Inside the power function. So u would equal x squared plus 1. So what's du? 2x dx. Everybody agree? 2x dx. Well, what do we have here? It looks like we have only an x dx. So what's that going to equal? If du equals 2x dx, what does x dx equal? 1/2 du, right? We would just isolate. All we do is we just isolate the part that we have. That's how I always do it. I think that's a good way to do it. And then this is what our substitution is going to be, right? X dx equals a 1/2 du. And so now what do I do with the 1/2? Pull it out front, absolutely, right? So then we get this. We get that, right? Right? Oh, which is equal to that. Agreed? Okay, but look what we did. We made a substitution from x's to u's. Our original limits of integration were in terms of what variable? Those were values of what variable? X, okay? So we've got to change the limits, right? And how do we do that? Well, we just go back to our substitution equation. That's what relates u's to x's. All we have to do then is ask ourselves, okay, when x equals 0, what does u equal to? 1. Okay, so then we know that our lower limit is going to change to 1, right? When x equals 1, what does u equal? 2, right? 1 squared plus 1 is 2. So look what we did. This is amazing, right? Now we changed this integral, this definite integral in x into an identical definite integral in terms of area, in terms of u. The integrals look different. If I look at those functions, the graphs, as we're going to see, are different, but the areas are the same, which is pretty amazing, okay? Do you see my point here now? We don't have to, in our indefinite integrals, we always had to get a solution in terms of u and then reverse the substitution to get back to x's. Because what is the solution of an indefinite integral? It's a family of curves, right? It's a function, right? It's a family of curves with a c involved, right? So like in the last example, I didn't say that very well. The last example was the family of curves, 1/2 arcsine 2/3 x plus c. C could be any value. There's an infinite number of values of c, so there's an infinite number of solutions, but together they just make up this family of curves that are just vertically offset graphs of this one, right? Everybody see that? So I have to reverse the substitution because my answer is going to be a function of x, right? So I got to get back to x's. But when I'm dealing with with a definite integral, my answer is just a number. It's an area under a curve. So there's no reason for me to go back to x's. I could, but don't. Why would you? Right? I could solve the integral and then reverse the substitution and go back to those, go back to my original limits of integration. But why do that? Why have to even bother going back? We chose u for a reason, because u is going to make our function simpler to deal with, right? It makes the expression more compact and easy to work with. So why bother going back to klutzy old x's? We don't need to, right? So what is the antiderivative of u cubed du? U to the 4th over 4, right? Okay, so then what's that mean? Well, with the u to the 4th over 4, we could pull the 4 out front. Did I do that? Yeah, I did. Good. So we pull the 4 out front, and I just get 1/8 u to the 4th from 1 to 2, because those are my new limits of integration in terms of u, right? So that just gives me 1/8 times 2 to the 4th minus 2 to the 1. Well, that's just 16 minus 1, so I get 15/8 as my answer. How about that? That's pretty cool that it works that way. Okay, let's look at, like, here's an example. So this represents the area under the curve. This is our original function, isn't it? Right? This was our integral. The area under the function x squared plus 1 cubed, quantity cubed, times x dx, or times x, right? So there's my integrand. X squared plus 1 quantity cubed times x. We're going to add up the area from 0 to 1. Okay, so there it is, right? There's my function, and the area is 15/8. Okay, everybody see that? Okay, if I change the value of a, I'm going to change the total integral, right? Say it again. Okay, let's look at that. Get that back to where it was, right there. Stay. Okay, so now that's what the integral looks like in terms of u, right? Isn't that what we got? 1/2 times the integral of u cubed du from 1 to 2. So it's a much easier graph. Now we're just looking at the area under the function u cubed from 1 to 2. And what do you know? It's the same area. Even though the two graphs look completely different. As we can see, if I superimpose the two graphs, there they are, right? They look completely different. The limits of integration are different, but the areas are the same, and that's all we care about. So this is another example of where we're going to solve a calculus problem by trading it for an easier problem that happens to have the same solution, right? We do that a lot in calculus. Okay, let's look at one more, this guy, and then you guys are ready. Okay, obviously we need a substitution, right? That's clearly not on our list of standard forms. So what's our substitution going to be here? Yeah, it's got to be log x, doesn't it? Everybody, give me thumbs on that. Everybody agree that the substitution would need to be log x? Okay, because for a couple of reasons. But when you look at this, you think, okay, well, it's contained inside the power function hand to the seventh. So that's a pretty good bet that's going to be it, right? Okay. Plus, the derivative of log x is 1 over x dx, isn't it, right? So we can see there's our du. Perfect. Okay, so we make our substitution then. U equals log x. So du equals what? 1 over x. So I can just call that dx over x, right? So there's my du, and there's my u to the seventh, right? Okay, that's way better, way easier looking integral, isn't it? So we get the integral of dx over u to the seventh. So why don't I just write that as u to the negative seventh, right? Everybody agree? U to the negative seventh du. Okay, but now I got to change my limits, right? Because I flipped from x's to u's. So what am I going to get for my lower limit? One, right? When x is e, u is 1. U is the log of e, which is 1. How about this one? What's the natural log of e squared? 2. Look at that. Question?
So when you convert, you just plug it back into u.
Yeah. Yeah, we just go back. Here's the relationship governing the transition from x to u, right? That relates u to x. So if I want to find corresponding values of u, I just go to my substitution equation. And then this is easy, right? This just tells us we get, what is that? U to the negative 6, 1/6, or negative 1/6 u to the negative 6th. Right? Everybody agree? From 1 to 2. So that's equal to negative 1/6 times 2 to the negative 6th is 1/64th, minus 1 to the negative 6th is 1. Did I do that right? Yeah, right? So then we just get 63, we get negative 1/6 times negative 63/64. And what could I do here? I could simplify a little bit, couldn't I? I could turn that in. I could divide each of these by 3 and get negative 21. Make that a 2. So my final answer just looks like negative times negative is positive. So 21 over 128. Okay. And we could check it real quick. Like if I just go into Desmos, let's see. If I just want to go into Desmos, I could check this, couldn't I? Do our original integral. You have to put the dx at the end, I think, probably in Desmos. Oh, whoops. Yeah, see, it's got to be out there. And is that what we got? Yeah, 21 1/28. Okay. Good? Oh, yeah, I had one more. When are we? I'll get through this one. Yeah. Yeah, I just evaluated it, right? We get negative 1/6, we can pull out front. 2 to the negative 6 minus 1 to the negative 1/6. What's 2 to the negative 1/6? 1/64. Well, because that's what I do. I evaluate it, right? I'm my definite integral by the fundamental theorem, right? That's the value of u, right? Remember, we transitioned our limits. Okay, make sense? Okay, what about this one? What would we probably do here? We might need to. The reason I put this one up here is this might be an example where it might be convenient. Well, now we just kind of did one like that already, didn't we? What would your u-Substitution be here? Probably not, because we don't have our du then would involve x's, which we don't have. What form does this look like it could match? Okay. Does that make sense? This would be an arc sine, wouldn't it? Right? It's matching a squared minus u squared. So what would u be then? U would be 8x, right? Because 64x squared is the same thing as the quantity 8x squared, right? So we would just let u equal 8x, which means du is 8 dx. And so dx would just equal 1/8 du. Everybody see that? Right? And so, I mean, we'll run out of time, but let's end it there. We'll finish this guy up next time before we move on to anything else. Okay. So I'm going to put an assignment up, and I know you guys are